all of the class is being recorded on Panopto, so you should be able to see anything that, in case if you missed anything or want to review anything. Okay, so the transient analysis. What do we mean by transients, and why the transient is important? Okay, transient means something temporary, something happening for short period of time, that something does not stay forever. And as an example of transient mode, or transient analysis, whatever, no matter what, is it electrical engineering or something else, which is, like imagine that you are traveling in the airplane. So the airplane, most likely, it will be in the ground. Then they say, you are ready to take off, right? So before taking off, they are in the ground, right? Then it will clear to take off, then it will take off until reaching a certain elevation. Is it, for example, 50,000 feet, whatever, 500,000 feet, I'm sorry, whatever. Then when it reaches at this distance or at this elevation, so you will see it will reach this elevation, for example, within 20 minutes, something like that. So that's why during this 20 minutes, it's the most dangerous thing. That's why we say you need to put seat belts, because for your safety, right? After that, it will remain on that elevation, and it will keep going for 2 hours, 3 hours, whatever, 5 hours. Then when it's ready to landing, they will say, put seat belt on, then for landing, right? Then also another 20 minutes, and here, for example, 4 hours. So look at this period. So landing and taking off are short period of time, right? And those are we consider as the most dangerous thing, or which is basically you need to put seat belt, and there are a lot of protocols to follow. Then the overall trip, for example, 5 hours trip, you will see only 20 minutes and 20 minutes. So these are considered short period of time. And what's happening inside this? It's the transition between the ground to that steady state elevation. So when it's reached to that elevation, which means it reached something we call steady states, this is a new states, then they will say you are clear to remove the seat belt and you can walk in the airplane if you want, right? So during this small period of time, you are restricted to keep seat belt on. This is called the transient period. And with respect to the whole trip, it's short period of time. Then the landing, the same thing, short period of time. So I will say that before taking off, we are at steady state. When reach that elevation, we are at steady state as well, because now we are in safe zone, then everything is good. Then after landing, we are at steady states. So what matters with us during transition period, which is when I go from high to low or low to high, whatever, like from ground to 500 or 50,000 feet, whatever. So this is considered as transients. And it is short period of time, something temporary, transients, which is, it's not the whole trip I'm going up or not the whole trip I'm going down, it's when to reach a certain elevation. So the transient, something temporary. That's the first thing that we need to realize. The other thing, which is something happening for a short period of time. Third thing, which is here in the transient, it's the most dangerous thing, or the things that we need to really be careful and make sure everything's fine. Okay? So that's an example of the transients. Now, how can we apply this in electrical engineering, or what's the point of the transient analysis in our course? So most likely transient analysis will be related to the storage elements. Storage elements, as we know for the circuit elements, we have resistor, inductor, capacitor. We used to say in DC, resistor remain as is, capacitor is short, inductor short circuit, capacitor open circuit. That's what we used to do. But right now, I'm going to add another condition. Yes, it's short circuit or open circuit if and only if it is fully charged. And the same thing, if and only if it's fully charged for the capacitor as well. In other words, the inductor, yes, it is short circuit, but it happens if and only if fully charged and in DC. Fully charged and DC as well. Okay? Otherwise, it is not short circuit. Okay, so what's going on? What's happening? Sometimes the inductor can be, or the capacitor can be charged or discharged, depending on the situation. So the transients means something for short period of time. Short period. Happens for short period. And the transient, there must be an action for the transient. For example, let's go back to the airplane. When it is, there should be an action, which is landing or taking off, going from high to low or low to high. So there should be an action in electrical circuit analysis that makes the transient to occur. So let's assume if I connect my capacitor or inductor, whatever, like here is a source, here is resistor, and here is inductor. For the normal situation, or we assume at steady states, since the source is connected to the load, then we will say we are at steady state, then inductor is short circuit because we are at steady state. And steady state, I'm going to make it a shortcut as SS. So it's short circuit because we are at steady state. Then, how can I know there is a transient or there is something, which is there must be an action. That action will be donated by a switch, which is basically, we will say that here is a switch, here is a resistor, here is an inductor. Now, in this situation, it's not short circuits. The inductor is not short circuits. Why? Because we have a switch. And that switch means there's a switching action. So the switch will be on, then the inductor starts charging. Switch off, it will be discharged. And so on. On charging, off discharging, and so that's what's happening. So whenever we have these kind of things in the circuit analysis, this means, or whenever we realize there is a switch, this means we are in transient mode. That's how I realize that my circuit is transient circuit or it is something else. It's not transient, it's steady states. So that's the first important thing, which is locate, is there any switch in the circuit? If yes, it's a transient circuit. If no, it's not transient. So I just solve it as chapter 3 and chapter 2, what I learned from chapter 2 and chapter 3. While whenever I see a switch, it's transient. Okay, that switch, again, says that when you turn it on, it will take some time for the capacitor to be charging or discharging because it cannot be charged instantaneous. It looks like when you put your cell phone into the charger, it will not reach to 100% direct. It will take some time, right? Charging period, right? Then until reaching that thing, which is reached steady state, reaching, for example, 100%, and if you keep it on the charger, it will reach 100%, and it will do nothing. It will remain. It will stop charging by itself. So there is a charging period, and the same thing, when you disconnect the switch, sometimes it can be connected to the other loads, which will make it discharging. Okay, does this make sense? Okay, let's go to the notes. So every time we assume the circuit operating at steady state unless we see an action. That action happens when there is a switch, and that switch changes its status. Most likely, we will assume it's changed its status at t equals 0. That's our target. Whenever, to avoid this, to make the simplification, the switching action happen at t equals 0. Then, it will start either charging or discharging for a short period of time. So the transient period is called transient period. And that transient period, we estimate this to reach the steady state. So the steady state happens after the end of the transient period. That transient period, we donated it by 5 times time constant, which is 5 tau. What's time constant? We will learn this later. So we estimated the charging time by 5 tau. Now, the switch has nonlinearity because it will be either open or closed. How can we solve this thing? Which is basically whenever we have, remember, in the inductor we have VL equal L di by dt. For the capacitor, we have IC equals C dV by dt. So in this situation, we need to use differential equation because it will be charging and discharging. The derivative will no longer be 0 because it's no longer constant. We have a switch, we'll make it on and off, then they will be charging and discharging. How to solve this differential equation, or how the weight, or what's order will be depending on how many storage elements. If you have only, and now when I mean by storage, when I say storage element, I mean by either inductor or capacitor. So when I have inductor or capacitor, so if I have one of them, one storage element, then you will have only first order differential equation. Whenever I have two, second order. More, higher order differential equations. So it will be more difficult, higher differential equations when we have a lot of things, which is a lot of or we call it storage elements. Again, storage elements, inductor or capacitor. When we have a lot of inductors or capacitors, you will have a lot of, or much complicated differential equation. How we can solve this differential equation? We have two ways. The first way using time domain, like integral and derivatives. I think you've learned this from differential equation course. And there is another way using the frequency domain, or in other words, Laplace transformation. I think also you are familiar with this from math, differential equation course. However, in electrical engineering courses, we prefer to use Laplace transformation. It makes the life much easier. And that's what we are doing in electrical engineering course in circuit analysis. We used to use Laplace transformation. Then we can do any complicated circuits using Laplace because the derivative will be, for example, S operator, S times L, then do Laplace, then Laplace inverse, something like that. And while in this course, we will want to make it easier for you. So we will we'll make some assumptions such that there will be only one energy storage. So you will see only first order differential equation. You will not go to second order differential equation. So that's the first simplification that we will make it. So you will either see inductor, single inductor, or single capacitor. You will not see multiple inductors, multiple capacitors. So our course is not circuit analysis, so we don't want to make it too complicated. Then let's make it as easy as possible. So, and our target is to prove the concepts, not to challenge you by complicated circuits. So there will be only single inductor or single capacitor, it will be called RL or RC circuits. That's what we mean by single inductor or single capacitor. And it will be only first order differential equation. That's the first simplification. The second simplification, we will assume some analysis, some standard to solve the analysis, or some procedures to solve the circuit, which we'll see it in worksheet number 6 and 7. You can, after today's lecture, you can have a look at it. I think the worksheet number 7 will be associated with RL, which will not be included in the first exam, but worksheet number 6 will be RC. You can have a look at it after today's lecture. So it will tell you some procedure in how to solve this circuit without the need to go to differential equation techniques. So we didn't need to go to Laplace transformation. You didn't need to go to differential equation. So here we are trying to make it much easier, then avoid using homogeneous solution or the other part of analysis or Laplace transformation. Again, we want to make it easier for you. So by following the procedure, you can solve the example, or you can solve that problem. This procedure, you can write this in your note sheet in case if you need for the exam. And the note sheet, you are allowed to have a 3x5 note card. Okay, so we here in our assumptions, or we will assume that we have ideal switch, which means it's open instantaneous. We have open switch or closed switch. So you need to be familiar. What does this mean? Because most likely, whenever you see this simple, you need to know what does it mean whenever we solve the circuit analysis. This switch means it is normally open and it will be closed at t equals 0. So the arrow means means the action. So the action will happen at t equals 0. In other words, when we say at t less than 0, the switch is open. At t larger than 0, the switch is closed. Okay? So again, the arrow means the action. and look at the initial status, it's open, then the final status is closed. However, the second stage, the initial status is closed, the final status will be open. So the arrow means the action, and t equals 0, the action happened at t equals 0. So when t less than 0, it is closed. When t larger than 0, it is open. Again, it's very important when you look at the switch to determine what it is. So sometimes it will not tell you what's the switch status. It will tell you solve the inductor current or solve the capacitor voltage, something like that. Then you need to know it by yourself. Okay? Again, look at the switch status and determine what it is. Okay, let's look at the transient circuits as this one. So we need to plot Vx of t, Ix of t for this circuit. Now with this one, is there any storage elements? Energy storage element. Again, I mean by energy storage elements, inductor or capacitor. Is there any energy storage element here, any inductor or capacitor? No. So since there is no storage element, no inductor or capacitor, this means there is no transients. Even though there is a switch, it will mean no transients. How? How can I prove this? The transient means charging period or discharging, right? So is there anything to be charged? No. Anything to be discharged? No. Okay. But we have a switch. The switch can create something, but it will not do the transients. Okay, let's see. Let's see when t less than 0. When t less than 0, the switch is normally open. And it is open. So let me draw the circuit. Here it is. I'm going to draw with other color. VDC. Ix of t. Here is the resistor. Switch is open. Here is R2. This is R1. Now, we need to calculate the currents and the voltage. And the voltage, let's say it's the voltage at the R2. Here is Vx of t. Okay? Now, by looking at this thing, what's the value of Ix of t will be? What do you think the current's value? Come on, what do you think the current will be? Is it V over the sum of R? Or let's recall, is it a closed circuit actually? It's open path. So whenever it's open path, the current will be 0, right? That's the first thing. How about the voltage? Vx of t equal Ix times R, right? Is this correct? Yes. Now I is 0. What will happen to R? Or what will happen to the V? 0. So the voltage is 0. So initially when t is than 0, it is 0. Okay? Now, the second thing, which is when t larger than 0. Okay, what will happen? Let me redraw the circuit. It's the same circuit, but it will be closed. The switch status is closed. It's closed. Here is plus minus Vx of t. Here is Ix of t. Now, what do you think for the currents Ix will be? Will be V over the sum of the resistors, VDC over R1 plus R2. Is this correct? Yes. How about the voltage? Vx of t will be Ix times R2, which is going to be VDC times R2 over R1 plus R2. Or you can do current voltage division to find it, whatever. It's the same thing, same answer. Now, if I need to plot the waveforms for Vx and Ix, here is the plots. Let me say this is Ix of t. Here is Vx of t. Now, when t less than 0, both the currents and the voltages were zeros. So Ix was 0, then at t equals 0, it was moved to be VDC over R1 plus R2. Vx, it was 0, Then at t equals 0, it was VDC times R2 over R1 plus R2. So that's how they look like. By looking at the waveform, you will see the transition happened instantaneous. It moved directly from, for example, 0 to be VDC over R2 plus R1. Happened instantaneous. And that happens if and only if we don't have energy storage elements. So we say that there is no transients because no inductor or capacitor. That's what it makes it like this way. Okay? Now, let's go to another example where there is an energy storage element, which is there is capacitor as an example. Let me give you time to write, then we will go to the next one. Okay. Here, we realize where is a capacitor. So there is an energy storage element. So in this situation, it will go from one side to the other side. But in this situation, it will be what's called it will take time to go to the next stage, because when you turn on the switch, capacitor will start charging. Okay, let's try to make the observation. So let's make it first thing when t less than 0. At t less than 0, I'm going to redraw the circuits by making it open. The switch is open. VDC. Here is Ix of t. Here is R1. Switch is open. Here is R2. Here is the voltage at the capacitor. Here's capacitor. And plus minus Vx, which is the same as the voltage at the capacitor. Okay. So in the first thing, when t less than 0, what do you think about the current? Is there any voltage? Is there any current flowing? No, because it's open path. So Ix of t equals 0. What will happen to Vx? 0 as well. So that's the first thing, which is everything is 0. Now, when t larger than 0, the switch will be closed. Here is VDC. Here is R1. Here is Ix of t. Switch is closed. Here is R2. Here is capacitor. So initially there were zeros, right? Now what will happen? Ix will no longer be 0. It will flow as a current, will go here and splits here, such that here is I1, here is IC, or I2, whatever, right? The current will split. So what will happen here? This will make the capacitor start charging. Starts charging. So for the voltage waveform, we expect the voltage, it will be initially 0. It will not go directly to a certain value, which is VDC over R1 plus R2 times R2. Here is Vx of t. It will not reach to that value instantaneous. It will take time for the charging. And that time can be calculated as 5 tau. What's 5 tau? We will learn this later. Take time, it's 5 tau, and this is called the transient period. So it's not like the previous example. Previous example, it reached instantaneous. Now it will take time. Why it will take time? Because the capacitor will start charging until reaching t equal 5 tau. That's the time when the capacitor will be fully charged. So when the capacitor will be fully charged, after whenever we say at t equal infinity or equal 5 tau, capacitor is fully charged, then what will happen? Capacitor replace capacitor by open circuits, which will make the equivalent circuit like this. Plus minus VDC. Here is the switch. Here is R2. Here I forgot R1. Here is R1. Then the capacitor will be open circuits. When t equal infinity or 5 tau, theoretically, the capacitor will be fully charged at t equal infinity. Practically, it will reach at t equal 5 tau. That's one difference between us as engineers and the mathematicians. So we have defined the infinity as 5 tau. And actually, we used to define t equal infinity as very long time or long time. But that infinity depending on our parameters or our case. So we can define the infinity as 1 second. We can define the infinity as 1 millisecond. It can be fine. That can be fine because most likely we would like to look at the capacitor when the capacitor will be fully charged and fully discharged. And why it's actually 5 tau, why not 3 tau, why not 6 tau? Based on several calculations, I don't think we have time to do it, but actually we will realize it will reach 98% of being fully charged at t equal 5 tau. And for us, we said 98% can be acceptable as fully charged. Because again, theoretically, it will reach 100% at t equal infinity, but we don't want to make it that long time, so we defined our target as 98%. If, for example, someone, or there's some approach that some people, they did t equal infinity or defined the infinity at 59% or 95%. So at 95%, it will take 3 tau, 3 times constant. But whatever, we find the most optimal situation is at 5 tau. That's why we selected 5 tau, not other values. Okay? So in this situation, we defined here t equal infinity as 5 tau. Then the capacitor is fully charged. Then it will reach a new state. So the transition, what's happening here is something important because I need to make sure everything is all right. No problem happening with my system. So during this transition period, I want to guarantee there is no overvoltage happened, there is no overcurrent happened, there is nothing will be burned out practically when we do something analysis. As a practical example of what's happening in real life for that kind of switching, when there is some power lines are out of service. When there are power lines out of service and we need to restore these power lines, then these power lines initially will absorb a high amount of currents. That's why sometimes when you see power restoration, you will see a light flicker. Or whenever you see a power outage, you will see the first thing, something like wrong with the lights or something wrong with the machines that turn on. So here, we need to make sure when you make some power restorations or power outage, we want to make sure this will not impact the customers, not impact the electrical utility equipments which are very expensive. So we need to make these kind of protections. So this has been used a lot as an example for protection purposes and electrical power utilities. And also it can be used, or we can also notice this in for example, if in your home, maybe in old homes, when there is, you connect the air condition and the air condition is starting suddenly, you will notice some flicker and light flicker. I'm not sure if you face this, but before we used to see these kind of situations, like light flicker or light will not be more efficient just for few seconds or maybe 1-2 seconds because there is something turned on that consuming a lot of power, a lot of currents. And this happened only for a short period of time because the air condition or the refrigerators or these kind of equipments are based on inductors. Inductors are energy storage elements. So what's happening initially when you turn on the air condition or turn on the refrigerator or whatever, the first thing, it will consume a high amount of currents, so the equivalent inductance will be fully charged. So it will take, that's why also sometimes you'll notice the noise higher than it will go back to normal. So it will consume a lot of currents to make it fully charged. Then when it's reached the steady state, it will back to normal. And even if you have a generator, and like a mobile generator, and try to, for example, use some machines, motors, or use, for example, some pump for inflatable, doing something like that. So if you turn on that pump initially, you will see the generator speed is moving like this, because it will absorb a high amount of current as a startup, which is called high startup currents. And the main reason for that, because the equivalent inductance will take time to be fully charged. When it will be fully charged, then it will be working as normal without any problems. So we are worrying about, during this 1 second or 1 millisecond, what's happening here? We need to make sure the system will be stable, there will be no problems in our operation. That's why we are studying this. Now, again, for our class, we will assume we are in DC. We will not discuss AC transient. AC transient is actually some courses like will be taught in grad level, so don't worry about it. We will assume only the switch that changed its status only once, which is at t equals 0. So you will not see it will be changed at t equals 0, then t equal 1, then t equal 2. Don't worry about it. It will be changed only once. DC circuits, only one switch that changed its status once, and only one energy storage element, which is either inductor or capacitor, and there must be with resistors. So it can be multiple resistors, 1, 2, 3, 4 resistors. So that's why we will call it RC for resistor and capacitor, or RL for resistor and inductor. So R for resistors, and it can be multiple resistors, C for single capacitor, and R for multiple resistors, L for one inductor. So now we will divide this chapter to be two things: RC circuit or RL circuits, whenever there is capacitor or whenever there is inductor. So there will be different procedure for each one. So this is number 1, RC, and later we will go to number 2, which is called RL. So it will be, each one has its own procedure, and they are different. Okay, what's RC transient circuits, or how we can solve it? To avoid the confusion or to avoid the complexity by going to Laplace transformation or using the differential equation, completed solution, homogeneous solution, other stuff. So we will try to avoid using this here. Therefore, we will assume the general solution, which is, the solution is well known, this one. This is the solution. So we'll assume we know the solution. The capacitor, it is RC circuits again, and the capacitor we know IC equals C dVc by dt. So the first thing that we need to do for the capacitor, we need to calculate the voltage. If you need to calculate the current, then use the other equation. So we have this equation number 1, this is equation number 2. These two equations are important. So again, whenever you need to calculate the current of the capacitor, you need to calculate the voltage first, then do the derivative. Okay? If you need to calculate the voltage, then just use number 1, that's fine. If you need to calculate both voltage and the currents, say the current will be the derivative of the voltage. So, again, whenever you need to calculate for the capacitor, do the current or do the voltage first. Then, by looking at this one, you will see we have 3 unknowns: Vc of infinity, Vc of 0, and tau. So we have 3 unknowns: Vc of infinity, Vc of 0, tau. If we figure out a way in how to find these 3 unknowns, then problem done. Then that's it. You are solving the questions. If you know how to find Vc of infinity, Vc of 0, tau, then you can find Vc of t. After that, you know how to apply the derivative, and there's exponential, so you know how to do the derivative of the exponential, then you can find IC. How to do that? Let's go to worksheets number 6. Go to Files, Worksheet number 6. Summarizing the procedure. I encourage you also to write the procedure in your note sheets whenever you go to the exam, so you can have an idea what to do. in order to find these three unknowns, again, like as I mentioned, we have three unknowns, Vc of infinity, Vc of 0, and tau. We need to know Vc of 0, Vc of infinity, and tau. So, three unknowns, they need to have three different circuits. Three different circuits. They are not related to each other. Step number 1, different than step 2, different than step 3. Step number 1, we will use it to find Vc of 0. Number 2, to find tau. Number 3, to find Vc of infinity. So number 1, what we will do, solve for t less than 0. T less than 0, we are at steady states. Like aircraft before being taken off. We are at steady states. The capacitor at steady state is open circuit because we are at steady states. Then switch at initial position before changing. If it is open, normally open. If it's closed, make it closed. Then solve for the capacitor voltage, Vc of 0. Solve it as DC circuit, which is, you can do KVL, KCL, Ohm's law, the same thing that we used to know. Okay? Then we find Vc of 0. That's the first unknown done. Assume initial switch status. Capacitor is open circuit. Solve it as any regular DC circuit to find the capacitor across, or the voltage across the capacitor terminals. Step number 2, we need to calculate tau, which is R Thevenin's times C. How to calculate R Thevenin's? We know how to do R Thevenin's, basically turn off sources. Any voltage source will be short, any current source will be open. The capacitor is open circuit. Then we need to calculate R Thevenin's across the terminals of the capacitor. R Thevenin's at the capacitor terminals. Then tau will be R Thevenin's times C. We know how to do R Thevenin's again by killing off the sources or turn off the sources, which make it again any inductor, any capacitor, any voltage source shorts, any current source open. Then find R Thevenin's across the capacitor terminals. This, after finding R Thevenin's, tau will be R Thevenin's times C. The last thing, which is to find Vc of infinity, draw for DC circuit for t equal infinity or 5 tau. Basically, here we'll assume at t equal infinity. Therefore, at t equal infinity, the capacitor open circuit because we are at steady states. What do you mean by t equal infinity? You can imagine that the aircraft reached that elevation, and now we are at steady states. Then the capacitor will be open circuit as well because it's being fully charged. Then the switch at final state, not initial state, then find the voltage across the capacitor terminal. So here, again, at t equal infinity, then we are at steady state. Solve it like as DC circuit, regular DC circuit. Then substitute this in the general solution. So IC will be C dV by dt if you need to calculate the currents. So next lecture, we will continue about what to do. So I encourage you to have a look also at the worksheet example.